got a pretty good idea of how these all work together. We'll just do more examples tomorrow. So we'll have all the basics out of the way today, and then we'll add a bunch of examples tomorrow. Yes, Zach?
So the homework assignment for 5.2 is not due until Thursday, correct?
Technically not due until Thursday. You should get on it. You should be able to get most of it done today.
And what about 5.3?
5.3 would be due on Friday. Okay. Yeah. Okay. So you should get done with 5.2 as quick as you can. I think you'll find that by the time we get done today, you'll be able to do most of the problems in each one of the sections. It might be a little bit fuzzy because we will not have done a ton of examples. That's what we'll be doing tomorrow. Okay? So on the starter questions, because this section is on rational functions, you should know what the root word of rational is. We talked about that a couple days ago. We'll talk about that again in just a second. But it says which fractions are proper and which are improper. So is this, careful here, is this a proper fraction?
Yes.
Answer there is?
Yes.
Yes, it is. It's not a reduced fraction, but it is a proper fraction, okay? So this one is 5/10 is. What about 3/2? Is that a proper fraction? Nope. Okay, so this is proper. This is improper. Now, what's the difference between the two of these? Why is one improper and the other one's proper?
Because that could be 1 1/2 and the other one is
Okay, so this one could be written as a mixed number. Okay, so you can have a whole number and a fraction to it. And this one right here, you can reduce it, but it's still just a fraction. Justin, what were you going to say?
Improper fractions are just above, like, are higher than 1.
Okay, they're equal to something more than 1. Can you tell me why by looking at this? Because the numerator's bigger than the denominator. The top's bigger than the bottom. That makes it improper. Okay? Now, what about this? Proper or improper? Okay, it's improper, but it's a different type of improper than this one right here is. Because they're exactly the same. The top and bottom are exactly the same. This is just a 1. So it's an improper, but it's a really easy type of improper. Because if the top is exactly the same as the bottom, we've just got a 1. Okay? So proper is the top is smaller than the bottom. Improper is the top is the same or bigger. Equal to or greater. Like the way you said that, just like a mathematician. Okay? Any questions? Okay, let's take a look at the second part. It says state the degree of each polynomial. So, is that tough to do? What's the degree here? Degree 3. It's not written, but the exponent there is a 1. And what is it right here? This would be degree 0, because if we had to put a power or an x with a power to it, it would be x to the 0 power. Everybody good there? Okay, so let's start doing the problems from today. The root word of the word rational is ratio. My gosh, it's the next word in line right here. A ratio is a fraction. A fraction is a division problem. So in these couple of sections right here, we're going to talk about rational functions, or in other words, functions that can be written as fractions, functions that can be written as ratios. And we're going to talk about how to graph them, kind of explore all the behavior. Okay, in order to get the graphs correct, so take a look, we're right here. So you just need to think about this. We've got to remember some basic graphing skills, how to find the domain of a function, factoring, simplifying fractions, and various other algebra and graphing skills. Pretty short list, right? Okay, that means we've got to remember a lot of things in order to get these right. Okay, we've got to keep track of tons of stuff here. Okay, the problems aren't really that difficult. If you'll pay attention, if you'll follow along, we're going to do this step by step. We're going to break this down so that we can figure out one thing, then we'll figure out another thing, and then we come back and we put it all together. Okay, so kind of like we did a story problem. We just kind of compartmentalized, figured out parts of it that weren't too difficult, and then we put all the pieces together. And this is really important right here. Okay, we're going to have to think about each piece of information we get. Okay, because there's a lot of logic that we can learn by dealing with rational functions. And again, it's not like somebody down the road is going to check you out at the grocery store and say, hey, before you pay for this, we're going to have you graph a rational function. Okay, you may or may not use this again very much, depending on how much math you take. You're definitely going to use it in this class. If you take 1060 and you take calculus or something like that, you're going to see this stuff again. But really what you want to focus on is the logic here. Can you get your brain to figure stuff like this out? If you can, you're going to be better at a lot of things throughout your life. So let's talk about what a rational function is. Let's define this. A rational function is of the form p of x over q of x. So it's a function on top and a function on the bottom, but they're special types of functions. They are both polynomials. Both of those are polynomials. And then we've got one little distinction here that we need to make, or one qualification that we need to make. This can be any polynomial we want on the top and any polynomial we want on the bottom, as long as the bottom is not what we call the zero polynomial. Okay? It can't be just a plain old zero. So the domain of a rational function, notice what we've done here by introducing division. We've introduced a domain issue. Okay? There's a problem there. We can't divide by zero. Okay? So the domain is the set of all real numbers except those that make q equal to 0. So if that denominator turns into a 0, not allowed. Okay? Something weird happens there, and that's what we're going to figure out in this section. Okay? So we're going to look at, to start with, we're going to look at a really simple and familiar rational function. Now, we didn't call it this at the time, but the function 1 over x, we called it the reciprocal function. That is a rational function because it's a polynomial on the top. It happens to be a degree 0 polynomial. It's just a constant. And on the bottom, I've got a degree 1 polynomial. Okay? So do you remember what this looks like? We've got this branch over here, and we've got this branch over here. And there were some important features that we drew on here. We graphed this point here, 1, 1, and this one, -1, -1. And then there were some other things that weren't really part of the graph, but we labeled them because it helped us figure out what the graph looks like. So this line right here, out near the ends, the graph comes down and approaches that line. And out near the end, the graph comes up and approaches it on this side right here. So does anybody remember what we called that? Okay, we called that a horizontal asymptote. That was y equals 0 was the horizontal asymptote there. And then we've also got this vertical line right here. So the closer we get to 0, the bigger this gets on this side and the smaller it gets over here. Remember we talked about the reciprocal of a small positive number like 1/10 is positive 10. So it gets really big over here and really small over there. That has a name also. That's called a vertical asymptote. And that would be x equals 0. So it says sketch the graph. There's a really good graph. We've identified the asymptotes and we want to talk about the domain. What's the domain on this one? Okay, everything except for 0. Anything else is okay, but 0 happens to be the one number that would make the bottom equal to 0. So we've got to throw that out. We said that's not in the domain. Okay, are there any questions? Okay, that's a rational function. Pretty easy one and one that you're already familiar with. Okay, but now we want to do some that are a little bit more complicated, and in order to do that, we need to learn a little bit of vocabulary. So the vocabulary is proper and improper, but it's not the type of proper and improper that we talked about at the beginning, although it's very similar. Okay, so if we have a proper rational function, then the degree of the numerator is lower than the degree of the denominator. The degree of the numerator is lower than the degree of the denominator. So let's take a look at this one right here. What's the degree of the numerator? 0. What's the degree of the denominator? 1. So is this a proper rational function? It is. Okay? So proper just means the degree of the top is less than the degree of the bottom. Okay? Now, improper. What would you think that means? The degree of the numerator is equal to or greater than. Equal to or greater than. So we're going to run through and here we're going to classify these. So we're going to look at the top, figure out the degree, look at the bottom, figure out the degree, and then we're just going to say, hey, is the degree of the top less than the degree of the bottom? Okay, if it is, we're going to say it's proper. What about this one? This one is proper. What about this one? This one is improper. Okay? They happen to be exactly the same, but remember, if it's equal to or greater, if the two degrees are the same or the top is bigger than the bottom, then we say that it's improper. And how about this one right here? This one is also improper. Okay? All right. So the reason we learn those words and the way to describe a rational function as proper or improper is because we can use those to find the horizontal asymptote. We can use those to find the horizontal asymptote. So figuring out whether it's proper or improper will help us find the horizontal asymptote, or something that we call an oblique asymptote. An oblique asymptote, we also can call that a slanted asymptote. So if somebody says this is oblique, okay, they mean it's slanted, tilted a little bit, okay? So, not really anything to write down here except for right here, okay? You just want to be aware of this, okay? This is something that you're going to need to know. This is part of that logic that we're going to apply. If the rational function is proper, then the horizontal asymptote is y equals 0. So if it's proper, you can immediately stop right there and say, hey, I know the horizontal asymptote is y equals 0. So we like ones that are proper, because the answer is just sitting right there. Now, if it's improper, it gets a little bit more difficult. There are actually two categories of improper, okay? So if it's improper, now I call this the good type. I made this up. If you're in somebody else's class, they might call it something different. But I call this the good type of improper because it's really easy to deal with. The good type of improper is where the top is the same degree as the bottom. If that's the case, then our horizontal asymptote is y equals the leading coefficient of the top over the leading coefficient of the bottom. I mean, that's it. End of story. So it's almost as easy as figuring out the horizontal asymptote of a proper rational function. It's just we've got to look at a couple numbers, find those. Okay, now I call this the bad type, and the reason it's the bad type is because it takes a little bit of work, and here's the work that it would take. Okay, if the degree of the top is higher, so if the top's degree 3 and the bottom's degree 2 or something like that, then it's the bad type of improper, and you have to use long division. That wasn't a cell phone, was it? Very good. Okay, so we use long division here. So it's going to be a little bit of a pain in the butt to find these, but the oblique asymptote is going to be y equals whatever the quotient is. That's going to be our oblique asymptote. It's going to be a slanted asymptote, generally speaking. Okay? So this usually produces an oblique asymptote, or you could call it a slanted asymptote if you wanted to. Okay? Any questions there? Okay, now you go ahead and hold on a second. We want to look at one thing before we flip the page over. It says, does the graph for example 1 fit the description for proper and improper? So let's look up here. What did we say this was? Was this proper or improper? We said it was proper. If it's proper, then y equals 0 should be a horizontal asymptote. Was it? It was. Okay, so it fits that description, and the asymptote works out to be the correct one. Now, go ahead and flip the page over. I'm going to leave this up here so we can see the bottom of that page and the top of this one right here. So here's all we need to do. It says find the horizontal or the oblique asymptote. So we're going to use this little process right here. We ask ourselves, is it proper or is it improper? So let's look at this one right here. What is it again? It's proper. If it's proper, then we know the horizontal asymptote is y equals 0. End of story. That's it. If it just says find the horizontal or oblique asymptotes, you look at it, you figure out whether it's proper or improper. If it's proper, y equals 0 is the horizontal asymptote. Done. Easy enough? Okay, let's take a look at this one. Okay, the question first is this proper or is it improper? Okay, if it's improper, then you've got to do this. You've got to figure out, is it the good type or the bad type? Are they the same degree? That's good. Is the top higher than the bottom? That's bad. What is it here? It's good. Okay, if that's the case, then y equals, remember what I said here? The horizontal asymptote is going to be the leading coefficient of the top over the leading coefficient of the bottom. Now that's assuming that we've done what we normally do in writing them down in descending order. So that's in descending order on the top and bottom. Degree 2 here, degree 2 here. I take the leading coefficient of the top over the leading coefficient of the bottom. So that's going to be 2 over 1. So y equals 2 is my horizontal asymptote. Questions there? Sure? Okay, let's look at the last one on part C. Sure we're good? Okay, proper or improper? This one is improper. Good or bad? Okay, it's going to be the bad, so we need to do, this is why it's bad, we have to do long division. Now, most of these are not that bad. They're not horrible division problems. So let's take a look at this one right here. What goes outside the box? Okay, x plus 2 goes outside the box. Now, could we do synthetic division on this particular one? You could do synthetic division on this particular one. Okay, I'm not a huge fan of doing that on these particular problems because this quotient that shows up right here, that's going to be our horizontal asymptote. So we're going to have to write it that way anyway, and some of them, they get a little bit ugly, okay, and maybe you can't do it using synthetic division, so you want to be a little bit careful here. So what do I multiply by? X. If I multiply, that gives me x squared, and that gives me a 2x, right? Go through and subtract or change the signs. So that's going to give me a minus x and a minus 3. You with me there? Okay, now, even though I said this is the bad type, and it kind of stinks that we have to do long division, it's actually not that bad. Because right here, what do I multiply x by to make it a negative x? I multiply by a negative 1. So I'm going to put a negative 1 up here. I could stop right there if I wanted. Okay. The slanted asymptote, we also call it the oblique asymptote, is y equals x minus 1. That's all that would be required on this particular problem. Okay, and I'm going to go ahead and find the remainder, and we'll talk about why the remainder doesn't make any difference on this a little bit later. If I go ahead and do that, if I multiply, I end up with, let's see, what have I got here? A negative x. That's going to be a minus 2. Then I'm going to change the signs. That's going to leave me with a negative 1. So if I were to write it out, it turns into this. This is the quotient. And what I'm saying is, this is all I need. That's all I need for the slanted asymptote. We're going to come back to that in a second. Okay? Give me a few minutes. We'll come back to that. But that's all I need right here. So what shape is this? If I were to graph this, what is it? It's a line. Where does it cross the y-axis? Negative 1. And what's the slope? Slope is 1. Okay, so it's going to look about like this. This is going to be our slanted asymptote. Out near the ends, instead of approaching some horizontal line, it's going to approach some slanted line. Okay? So we'll see that in a few minutes. Any questions there? Yeah.
So we're finding the horizontal asymptote, but is the vertical asymptote going to stay the same?
Yeah, we're going to do vertical asymptotes in just a second. That's what's coming up next. Okay? Good? Okay, you have problems in 5.2 that simply ask, what's the horizontal asymptote or what's the slanted asymptote? What's the oblique asymptote? And that's all you'd have to do. You don't have to graph anything. Okay, you just have to figure out some of that information. Okay? All right, so let's take a look at the next part. Okay, after we figure out what the horizontal asymptotes or the oblique asymptotes are, the next thing we'd want to do, generally speaking, is we want to find any vertical asymptotes, and then we want to find something called holes. So we want to find the vertical asymptotes, and we want to find any holes that might be in the graph. Okay? Okay, now the way we find vertical asymptotes and holes is we find the zeros of the denominator. Okay, now I don't think on your paper that's highlighted, but I would highlight it. We want to find the zeros in the denominator. Now, think about that for just a second. Zeros in the denominator. Does that ring a bell with anybody? Yeah, that's a domain issue. That's a problem. We can't divide by 0. Okay, that's what's going to produce holes and vertical asymptotes. Okay? So the number that makes the denominator equal to 0 is not in the domain. That's why we call it a 0 of the denominator. Okay? If that factor that produced that 0, if it cancels, so I'm going to highlight this, if that 0 cancels, then it becomes a hole. There's a hole in the graph right at that location. And if it doesn't cancel, then we're going to have a vertical asymptote. Now, I realize this is a lot of information. We're going to put this in practice in just a second. So this says, find the vertical asymptotes and or the holes for each of the following and state the domain. Tylin, you'll want to wake up for this. Very good. Okay. So the first thing we're going to do is we want to find the zeros in the denominator. Okay. So we want to factor this. So if I were to factor this, this factors to x minus 1, x plus 1, and the numerator is still x minus 1. Now we've done this numerous times. We've looked at functions to figure out what their domain is. What is the number that I cannot plug into this factor right here? Okay, x equals 1, right? And this one right here? X equals negative 1. Those are the two numbers that I can't plug into this. So the domain would be all the x's I want except for plus or minus 1. Those are not in the domain. I am not going to have a point on the graph there. Okay, now, what did we say up here? We said we want to simplify this and we want to cancel things off. We want to make this as simple as we can. Can I cancel anything? I can. I can cancel that one with that one. What that means is, at x equals 1, because that canceled off, I have a hole there. At x equals 1, I'm going to have a hole. Because this one didn't cancel off, that means x equals negative 1 is a vertical asymptote. So because this one canceled, it's a hole. Because this one sticks around, it's a vertical asymptote. It's literally that simple. Find where the domain issues are. If they cancel off, it's a hole. If they stick around, it's a vertical asymptote. Yeah.
How many asymptotes do you have?
Tons of them. We might have some with maybe 3. Usually we'll have 1 or 2. Sometimes we'll run into 3. Vertical asymptotes, that is. Okay. But you could have a ton of them. Okay. Luckily, they don't do that to us. Okay, any questions? Okay, let's take a look at this one right here. The first thing we want to do is we want to factor this. So let's go ahead and factor. So let's see. I'm looking at the top and I'm thinking that's kind of ugly. The bottom, though, I can handle that. Numbers that multiply to be negative 8 that combine to be positive 2. Positive 4 and negative 2. And then I need to look at the top. I need to factor that. Okay? I can figure out the domain the way with what I've got written, but I do need to factor that there. Okay? So, let's see. I could use that trinomial grouping method where I multiply the 2 and the negative 4 together and stuff like that. Or I could just do this. The only way that's going to factor is if I start out with a 2x and an x. And I need numbers here and here that somehow multiply to be negative 4 but combine to be positive 7. Multiply to be negative 4. Somehow I can put them together with that 2 to make a positive 7. So I'm going to put a 4 here, a 1 here. If I make this one negative and that one positive, this is going to give me positive 8. That's going to give me minus 1, so that's going to give me my plus 7x in the middle there. Does that make sense? Okay. Let's figure out the domain. What's the number that I can't plug in here? Negative 4. What's the number that I can't plug in here? Positive 2. So those are the numbers that are not allowed in the domain. Anything but negative 4 and positive 2 is okay. So all reals. You can plug anything we want into this function except for negative 4 and positive 2. Do either of those cancel? This one does, doesn't it? That one cancels. What does that mean about the graph at x equals negative 4? It means we're going to have a hole in the graph there. Just a little missing dot. And what does it mean about at x equals 2? We're going to have a vertical asymptote. So hole right here, vertical asymptote right there. Any questions? Okay. This one I think is just a tad easier because what's the domain? Not equal to negative 2. Okay, you can see that right from the get-go. Do you know whether it's a hole or an asymptote at negative 2?
Hole.
How do you know? Tell me how you know. We got 2 guesses here.
Because I factored it in my head.
Tylin factored it in her head. What does this factor to? Multiply to be negative 3, combined to be positive 1. Multiply to be negative 3, combined to be positive 1. It doesn't factor. It doesn't factor. Okay? So because it doesn't factor, is there any way that this is going to cancel? It's not going to cancel, so what happens at x equals negative 2? Vertical asymptote. Okay? Now remember what the instructions were. The instructions were find the vertical asymptotes and or the holes for each one of these and state the domain. So it's kind of a process we do all together. We say, hey, wait a minute, you can't use a 1 or a negative 1. So there's our domain. We throw those out. And then we figure out which one cancels. If it cancels, it's a hole. If it sticks around, then it's a vertical asymptote. Yeah?
So, taking an example from like the third one that we just did.
This one here?
Yeah.
Okay.
Would it be possible that we get a problem where it would cancel, or no matter what, we would have to have vertical asymptote?
No, there are graphs that don't have any vertical asymptotes. We'll do some that don't have any vertical asymptotes. We'll do some that don't have any vertical asymptotes or holes. We'll do some that just have a hole here or there. Okay. Some that have vertical asymptotes and no holes. Okay. All right. Any questions? Okay. So on example 5 is, we really don't want to forget some of the easy stuff that we've learned how to do, like finding intercepts, like the multiplicity of a 0, like whether it touches or crosses and things like that. Those are all really helpful. Okay, so if you can figure out those, then we'll be in really good shape. So let's take a look at this and let's figure out what the x-intercepts are. X-intercepts. How do you find x-intercepts? You set it equal to 0. Now, y-intercepts are important. We can find y-intercepts really easily. If you plug in a 0, what do you get on the top? A negative 1. And what do you get on the bottom? Negative 1. So what's the y-intercept? It's going to cross at 1. Okay, now that's helpful, but x-intercepts, we really like those. Those are important. So I want to find x-intercepts. So if I'm going to find the x-intercepts of this one, I'm going to set this equal to 0. But remember, you want to be kind of smart about this. Yeah.
You just set the numerator to 0.
Okay, so that's what we're after. I want to take this, and I want to look at how I simplified this. Whoops. I canceled that off. So this behaves like 1 over x plus 1. Now, when we say we're going to set this equal to 0, what's the only thing, as Parker said, that can make this fraction equal to 0? Just the numerator. So does 1 ever equal 0? Because that doesn't have any answers, we'd say no x-intercepts. So only the numerator can produce x-intercepts. That's the only part you have to worry about. But you do want to use the simplified form. If you can cancel something off, you'd want to use that simplified form. Okay, so let's take a look at this one. Were we able to cancel anything? Let's look up above because we already factored that one. This behaves like 2x minus 1 over x minus 2, right? If I set this equal to 0, what would the x-intercept be? Positive 1 divided by 2, so that's going to be 1/2. That's going to be our x-intercept. So no x-intercepts here. Crosses the x-axis at just one place. Yeah?
So we only look at the top.
Yep, only look at the numerator. Because if the denominator was 0, the whole thing wouldn't exist. We use the denominator to find the holes and the vertical asymptotes. We use the numerator to find the x-intercepts. Okay? All right, let's look at the last one. We want to set this equal to 0. Remember, it didn't cancel at all, right? We couldn't factor it. So Parker, what's the only part of this that I need to worry about? Just the numerator. So I want to know when x squared plus x minus 3 is equal to 0. If it doesn't factor, what are we going to use? Quadratic formula. So if you wanted to find the x-intercepts, we'd have negative 1 plus or minus. I'm going to do a little bit of work in my head. This is going to be 4 minus, or sorry, this is going to be 1 minus. 1 minus 4, and then a times c. 1 and negative 3 all over 2. Negative 1 plus or minus let's see, I'm going to be adding 12. So this is a 13 over 2. So this is kind of ugly, but here are the x-intercepts. -1 plus, whoops, -1 plus radical 13 over 2. And the other one is -1 minus radical 13 over 2. Now, luckily, that doesn't happen very often. Usually, they try and make these pretty nice. Okay. Any questions? Okay. All right. So, see this big ugly box here? Okay. These are all the steps that are required to graph a rational function. Looks like a long list. Okay. Now, you're not going to memorize this. You're going to understand this list. And you're going to be able to, you're just going to go through this process, because basically we've gone through and we've done every one of these things. The only thing we haven't done is put all this information together to do the last step. Okay? So we want to put these together and sketch the graph, and we want to label important features. Okay? Let's see. So we're going to talk about proper and improper to find the horizontal asymptotes. We're going to factor the domain, figure out which ones cancel. Do we have holes or vertical asymptotes left there? We're going to find the x and y intercepts. We're going to draw the asymptotes and locations where we're going to have holes, and we'll put all that information together in order to graph them. Now, a lot of people like doing that list step by step by step. Okay? You can do that. Some people find it easier to just do each step, graph that, do the next step, graph that, and keep track of each piece of information that way. So we're going to start off here. So the first thing we want to do is we want to figure out whether we've got horizontal or slanted asymptotes. And the question there is proper or improper? Proper. This is the work I'd show for this. This could easily be a test question. Proper. Y equals 0 is a horizontal asymptote. Now, if we wanted, we could come over here and we could draw the horizontal asymptote right now. So, horizontal asymptote, y equals 0 is our horizontal asymptote. We'll label that. The next thing we want to do is we want to figure out, do we have any domain issues? What's the domain for this particular function? So this is x minus 1. I'm going to factor that so I can see what my domain issues are. My domain issues are at x equals 1 and at x equals -1. So the domain is everything except for plus or minus 1. Does anything cancel? I cancel this off. What does that mean about this? I have a hole there. What does that mean about this? I have a vertical asymptote there. So I'm going to draw, watch please, I'm going to draw a vertical asymptote at -1, so it's going to look like this. I'm going to label that. I'm going to say I've got a vertical asymptote at x equals -1. Then right here at 1, this is what I'm going to do for a hole. And you don't have to do this, but I find this makes it so I don't forget the holes. There's a hole right here. So I'm going to draw a short dotted line, and I'm going to write hole here, just to remind me. Okay, let's write down the simplified version. The simplified version is 1 over x plus 1. Okay, now if I slide back up here, I found the horizontal or oblique asymptotes. I figured out what the domain is. I figured out the vertical asymptotes and the holes. The next thing is something that we've done over and over and over again. We find the x and y intercepts. So I'm going to make a little xy table just like I told you on the first day of class. We're going to graph something and we want to find intercepts. Plug in a 0 for x. 1 on the top, 1 on the bottom, so I get a 1. If I plug in a 0 for y, that means I'm setting this equal to 0. So 1 over x plus 1 equals 0. What did we figure out just a second ago? It doesn't have any. There's none. Okay? You with me? So I'm going to come over here, and now I'm going to do this in red. I'm going to put this point on the graph. 0, 1 is on the graph. Okay, now my contention is we have pretty much everything we need to graph this. Okay, now stop and think about this for just a second. This is a vertical asymptote. That means when the graph gets close to it, now it goes through this point, right? Okay, I'm going to draw it this way for just a second. It's got a choice. It can either go up or it can go down. Now don't say anything out loud. I want you to think for a second because you're going to use this over and over and over again, and it's going to save you a ton of work. The choice is go up or go down. It can only be one of them. It can't be both. Who thinks they know what the answer is? Okay? And if you know what the answer is, can you explain why that is the only logical choice? There's an answer, and there's a darn good reason why that's the answer. It's either going to go up or down. Okay? Who can tell us and why? Katie. Awesome. We don't have a choice. It's got to go up like this because if it were to go down, it would cross the x-axis and that would produce an x-intercept. Now, if I come over here, I've got to have a little hole right there. And then it has to look like that horizontal asymptote out near the ends, right? Okay, watch. Just watch. Don't draw. Can it do this? Why not? Would produce an x-intercept, right? So it's got to do something like this over here. Notice I haven't even picked any points. The only point that I found on here was 0, 1, the y-intercept. Now, what does it look like over here? We really have two choices. It's got to run along the horizontal asymptote, and then when it gets close over here, it's either got to go up or it's got to go down. Those are our two choices. Here's how you figure it out. Anybody want to take a guess how you figure it out? Zach?
Well, we look at the parent function for the...
You could look at the parent function if you knew what this did. That's awesome if you can do that. Generally speaking, they're going to be a little more complicated than this, so what we're going to do is we're going to pick a test point. Pick any number you want. Clayton, what number do you want that's less than -1?
-3.
-3. Clayton picked -3. So we're going to figure out what is r of -3. We're going to plug in a -3. There's a 1 on the top, a -3 plus 1 on the bottom. So that's going to be 1 over -2. The answer is -1/2. So that means it goes through the point -3, -1/2. So if I go back to 3, I'm down here at -1/2. Do you know what it looks like now? If it goes through here, it has to go down. It can't go up for the same reason Katie gave just a second ago. That would produce an x-intercept. And out near the end, it's got to run along here and go like this. Now, watch. Could it have done this? Could it have strayed off down here and kept going? Okay. It can't do that because out near the end, it's got to look like this horizontal asymptote. Remember, that's what an asymptote is. Okay, a horizontal asymptote, it's what it looks like out on the ends. So its only choice is to do this. It could have, I won't lie to you, it could have done this a little bit, but eventually it's got to get back up there. Now, do you think it would normally do something weird like this? No, these are pretty well behaved. Okay, that's the graph. That is a rational function graph. Any questions? Okay, if you need to look at that list long enough to get these down, you can. But I think you'll be in pretty good shape if you just go through and think about this process here. So the first thing we want to do is, it's a very simple question. You're going to have some of these on the test. It's just one of two words. Is it proper or is it improper? Proper. Immediately you write down y equals 0 is our horizontal asymptote. We've got that piece of information. Next, domain. Let's factor this. 2 over x minus 3 and x plus 3. What can't I plug in here? And what can't I plug in here? -3. Do either of those cancel? They don't, okay? So they are not in the domain, and they are both vertical asymptotes. I'm going to put dotted lines around those. You with me? Okay, now let's go over here and let's start drawing this. So the horizontal asymptote is y equals 0. So I'll draw that. Y equals 0 is our horizontal asymptote. At -3, I've got a vertical asymptote, and at +3, I've got a vertical asymptote. Any holes here? Do I have any other information? Y-intercept's going to be pretty easy, right? Okay, so I'm going to make a little XY table. I'm going to plug in a 0, and if I plug in a 0, I get -2/9. So -2/9 is, and I'm going to change to blue here, -2/9 is right there. That's my point right there. Trevor, what do I do next? I just found the y-intercept. Find the x-intercept. Let's set this equal to 0. Notice that's the simplified version, and I've got 2 over... Well, I don't even need to write the bottom, do I? Does 2 ever equal 0? It doesn't, so none. Okay, now stop and think about this. This is huge. There are no x-intercepts, not a single one. What does that mean about the graph? It never touches the x-axis. Never does it touch the x-axis. Okay? So, there are, watch carefully here, there are 3 pieces to this. There's a piece over here, there's a piece over here, and there's a piece over here. All we need to do is figure out those pieces. My contention is you should know what one of those pieces looks like. Because if the graph goes through here, whoops, can it go up?
No.
On either side? Nope. So its only choice is it's got to go down. So it's got to look something like this. When you hit a vertical asymptote, you either go up or down. This one has to go down because we've got a point below the x-axis here. Now, the other ones, maybe not so much. In order to figure out what this piece looks like and what this piece looks like, you should know this. It's either up here or down here, right? And either up here or down here. How do you figure out which it is? Plug in a point. So we're going to plug in, let's see, Clayton, you want to do us the honors? You want to pick another x?
-4.
We're going to plug in a -4. If I plug in a -4, I've got 2 over, I'm going to plug it in right here. So that's going to be 16 minus 9. So that's going to be 2/7, right? So if I go to -4, I go to 2/7. So -4 comma 2/7. Well, what do you know? It's got to be here. That branch, we'll call it a branch, that branch has got to be here. Now, there's something cool about this particular graph, this particular function. What do you notice? Yeah, it's symmetric with the y-axis. This is an even function. It doesn't matter whether you go to the left or to the right, you're going to get the same shape. So if I were to plug in a 4, if I figured out r of 4, it's also 2/7. So I'm going to go over here, go to 2/7, 4 comma 2/7, and you better know what this looks like. It runs along here and it has to go up. So this is always going to be above the x-axis. That's what it's going to look like. Okay, I'm going to put arrows here. If this problem were on a test, which it easily could be on a test, this would be really good. I could be really convincing with one tiny extra piece of information. What's the only thing I haven't labeled? The y-intercept. I probably ought to put that that's a 0, negative, what was it? -2/9? Okay. If I put that on there, notice I've only got 3 points on this graph, and that is a ridiculously complicated graph, but we got it right. Yeah.
So, I'm just like, is this, how how come there's not a like gravel looking thing above the x-axis, right where it? Like,
I mean, why isn't there something
Yeah.
symmetric over here?
Starts on the bottom and can't cross the
Starts on the bottom and can't cross the x-axis, so there's no way it could go up. And you can't have both of these pieces. Can somebody tell me why you can't have both of those pieces? It wouldn't be a function. Got it? Still has to pass the vertical line test. It's still got to be a function. Any questions? Okay, let's take a look at these couple of thought questions right here. It says, can a graph touch a vertical asymptote? Answer there is no. It can't. It can't touch it because that places a vertical asymptote because it's not in the domain, and it was a domain issue that didn't cancel. You can't touch a vertical asymptote, okay? Wouldn't be a function. Not in domain. Can a horizontal asymptote, or excuse me, can a graph touch a horizontal asymptote? Well, let's look up here.
Yes. I'm saying that.
Okay? On that one it didn't. But we're going to have shapes that go like this, and it'll cross through. If you've got a horizontal asymptote of y equals 0, and you've got an x-intercept, it's going to cross through that horizontal asymptote. So the answer there is yes, that's okay, because remember what horizontal asymptotes are, okay? They are end behavior. They're what it looks like out near the ends, out near negative infinity and positive infinity. So we'll say it this way. Can it touch or cross a horizontal asymptote? Yes, it can, usually near the middle. Out near the ends, it's either usually above or below. There are some exceptions to that when you get to trig, but we're not in trig, so generally speaking, crosses near the middle. Okay, that's all I have for today. You'll notice that what we've got tomorrow is just a bunch of practice. So what you need to do is go home tonight and familiarize yourself with that. Read through the notes. This did record, so I'll post the video if you want to watch that again. Please think about it because we're really putting a lot of logic into this and figuring out why these shapes make the shapes they do. Okay? All right. Have a great day. Please get done with 5.2 by tomorrow if you can. Okay? It's not due, but if you can get done, that'd be great.